My name is Garrett Mitchener. I'm in the Department of Mathematics at the College of Charleston in South Carolina. My poster is about how to evolve a neuron. This is an experiment in artificial biology. The objective is to start with an abstract chemistry model that is capable of general computation and simulate the evolution of a neuron. Specifically, agents in the simulation should develop the ability to detect coincidences in an input spike train and exhibit spike timing dependent plasticity, which is thought to be a key mechanism in Hebbian learning. Each agent consists of one cell. Its state is a vector A, where A sub t equals n means that there are n molecules of type T in the cell. Each cell's program consists of a list of instructions of the following form. If A sub p switch is greater than or equal to a threshold, then add 1 to A sub p up and subtract 1 from A sub p down. This instruction format is designed to mimic transcription factors, which bind to DNA and regulate the expression of downstream coding regions. All instructions are evaluated once per time step, and the results are independent of the order in which they are evaluated. These instructions form an artificial regulatory network, which is analogous to the gene regulatory networks in living cells. Each agent's diploid genome consists of two pairs of bit-string chromosomes. Nucleotide bits from the chromosome are translated using a majority of 3 code into codon bits, which are grouped and translated into integers using a gray code. In this project, agents are trained on coincidence detection tasks. The input is a discrete time series. Each input spike sends a signal to the agent. When two input spikes arrive at almost the same time, the agent should generate an output spike of its own, otherwise it should generate no output. A biochemical mechanism thought to be important to Hebbian learning is spike timing dependent plasticity. If a neuron spikes repeatedly, its input synapses should temporarily become stronger, causing it to spike more readily. In living neurons, the NMDA receptor implements such a mechanism. In this simulation, after a period of high activity, an agent should spike after two input spikes arrive, even if they are moderately separated in time. After a period of low activity, an agent should reset itself and again spike only after pairs of input spikes that are very close. Each agent is rated on its performance on a long list of input spike trains. Each run of the simulation ends after the first perfectly scoring agent dies or after 20,000 generations, whichever happens first. Here is an example of a perfect solution. In this diagram, nodes represent elements of the state array A. Each instruction corresponds to two arrows, a solid arrow from P switch to P up, and a dashed arrow from P switch to P down. Only arrows relevant to generating output are shown. The overall structure is that input feeds into A3. As it increases, two instructions add to A10, and two more eventually turn on and add to A41, triggering an output spike. Many instructions subtract from A3, A10, and A41, thereby resetting the cell and preventing spurious output spikes. The reset process is slow enough that after a period of high activity, A3 and A10 remain high enough that the agent spikes after the arrival of moderately spaced pairs of input spikes. Some tasks seem to be more difficult, so should all of them be weighted the same? The software can be configured to scale the scores on tasks before adding them together into an agent's overall rating. Here I compare an unscaled sum, a sum where the weights increase with task difficulty, and a sum where the weights decrease with task difficulty. Note that a genome with a perfect score under one scaling variant also earns a perfect score under all the others. The risk of weighting difficult tasks more is that a genome may have a fitness advantage by earning partial credit on a difficult task at the expense of failing at a simple task. Such a genome is probably not on track toward a fully correct solution. Weighting simpler tasks more forces the population to solve the coincidence detection problem first, then incorporate spike timing dependent plasticity. The risk here is that the pressure to maintain the coincidence detection mechanism prevents the population from exploring the fitness landscape, thereby preventing it from discovering fully correct solutions. The data indicates that these things do happen. Here are charts for 100 sample runs under each scaling variant. The runs where tasks are weighted by increasing difficulty are the most likely to discover a fully correct solution, but the imperfect runs score poorly on the simpler tasks. The reverse tendency is seen in runs where tasks are weighted by decreasing difficulty. Please contact me if you are interested in this project or the software.